In this second lesson on this course on Lagrangians and Hamiltonians, we're going to be looking at how to construct a Lagrangian. That is, we're going to be looking at the rules on how to turn the kind of system you'll have seen in a normal classical mechanics course and how to construct the Lagrangian for that system. As with the last video, there is a booklet in the description for you to fill in as we go through the video. And as this lesson is going to be quite example question heavy, all the questions are written in the booklet with space to follow along with either. The Lagrangian for a classical system is just given by the kinetic energy take away the potential energy. But why is this? It probably looks like I've just pulled this out of nowhere. Well, the justification for it is that when we use this formalism, we get back to Newton's second law. And you'll see this explicitly with the examples. The equation of motion we get is exactly the same as the equation of motion we would get if we used Newton's second law. For some of them, it will be quite hard to see because they're using different coordinates. But for the ones in Cartesian coordinates, it should be quite easy to see. And then the first homework problem, you'll look at the Lagrangian more generally, and you'll see how it will always lead to Newton's second law. And then you'll also consider variations on the Lagrangian. And you'll see that this kinetic energy minus potential. For our first example, we just have the classic mass on a spring type system. We have a particle of mass m, a spring of length L, and this spring has spring constant K. We know our Lagrangian has to be kinetic minus potential energy. So let's look at the kinetic energy first. This is a half mv squared, where instead of v, we've got x dot, the time derivative of position. And then the potential energy, this is a half k times the extension squared, where the extension is x minus the initial length of the spring. And so our Lagrangian, it's a half mv squared minus a half k times the extension squared. And now we could have said that x equals 0 is the equilibrium position. We could have chosen different coordinates. This next example, I'm going to go through a bit quicker. So I recommend you pause the video, have a go yourself, and then come back, and then I'll go through it. So our Lagrangian is as normal, kinetic minus potential energy. The kinetic energy is a half mv squared. Except this time instead of x dot, it's y dot, just because we're going directly upwards. So I'm using y instead of x. And then our potential energy is gravitational potential energy, which is just mgh, or mgy. For the next two examples, we're going to use the Lagrangians we just worked out to find the motion of an object. So here we've got the spring being stretched, and then at t equals 0, let go. And we want to find how the mass moves. So as in normal classical mechanics, as in Newtonian mechanics, we want to find the equation of motion. Except now instead of Newton's second law, we're going to use our Lagrangian and the Euler-Lagrange equations. And we've written them here in terms of our variable x. And we apply this to the Lagrangian, and we get here our equation of motion. And you could rearrange this and see it is what you would expect from Newton's second law of a stretched spring. So now we want to solve this differential equation as you would in a normal Newtonian physics course. We have a constant term plus the sum of sines and cosines. And then we want to apply the initial conditions. So when t equals 0, the position is 2L, and this gives us A equals L. And at t equals 0, it's being held fixed, so the velocity is 0, and this gives us that B is 0. So our final solution is given here. As you would expect, the spring just oscillates back and forth around its equilibrium position. For this question, I would say pause the video, have a go in your booklet, and then come back to the video and I'll put the answers on the screen. So now you've had a go, let's quickly go through the solution. So firstly, we find the equation of motion using the Lagrangian and the Euler-Lagrange equations. And then we find the general solution to the differential equation. I mean, you may just recognize this from like the Suvat equation, because here acceleration is constant. And then we use our initial conditions. We get y as a function of t. However, remember that we're launching this from the ground, so eventually it's going to come back down and hit the ground. So we could say it hits the floor at t equals 2v over g. Initially, this pulley system might seem quite tricky with Lagrangian mechanics. However, after you get used to how to set them up, they're actually much easier in Lagrangian mechanics than they are in Newtonian mechanics. So let's start off by setting up our coordinates. So we're going to say y equals 0 is the middle of the pulley. And then the big mass is a distance y big M down, and the little mass is a distance y little m down. Now we've got our coordinates, we can set up our Lagrangian. So the kinetic energy is the sum of the kinetic energy of the big mass and the small mass. And similarly, our potential energy is just standard gravitational potential energy for both the masses. However, these particles are connected. They're connected by one piece of wire. So as one mass goes up, the other mass goes down. And we can express that by saying the sum of the two distances is equal to the total length of the wire. And this means we can rewrite y big M everywhere in terms of y little m. So our kinetic energy becomes again, it's still the sum of the two kinetic energies, but now everything is written in terms of y little m. And our potential energy can also be rewritten just in terms of y little m. And finally, this L isn't a coordinate, it's just a constant, so we can cross this out. Remember, potential energy is only defined up to a constant, and so if there's just a constant term, we can just get rid of it and ignore it. And so our Lagrangian is given here. We've got the kinetic energy, take away the potential energy. Then we want to find the equation of motion. This time we're only going to have one Euler-Lagrange equation. We've written everything just in terms of one coordinate, not two. There's in fact only one degree of freedom for this system. So we only have one Euler-Lagrange equation and only one equation of motion. So by applying the Euler-Lagrange equation, we get our equation of motion. And then we wanted to find the initial acceleration, so we can rearrange this to get our acceleration. We are now going to look at systems in more than one dimension, and so we're going to need to look at the kinetic energy in cylindrical and spherical coordinate systems and how we get there. So we're going to start off with the Cartesian kinetic energy, which is, as you'd expect, a half mv squared, where we look at the velocity in each of the three Cartesian directions. So firstly, let's look at cylindrical coordinates. So firstly, we have x is r cos theta, y is r sine theta, and then z is just z. And then to get the velocities, we take the time derivative of each of these and use the product rules and chain rules where appropriate. So we have our x velocity, which can be written in terms of r and theta, our y velocity, and our z velocity. And then we substitute these in to the kinetic energy formula above, and we get a simplified result. All of the sines and coses cancel. And these first two terms at the front, these give us the radial velocity and the tangential velocity. And you may have seen these if you're used to dealing with mechanics in these coordinates. We are now going to move on and look at spherical coordinates. Now the method here is exactly the same, but the algebra is a bit more involved. So firstly, we're going to write x equals r cos phi sine theta. And here we're going to use the physicist convention that phi is the azimuthal angle that goes from 0 to 2 pi.
and theta is the polar angle that goes from 0 to pi. And then y can be written similarly, and then again for z. And then to get the velocities, we differentiate these, use the chain rule and product rule where appropriate. And I'm not going to put these on the slide. The algebra is very long and tedious, just differentiating quite a few times. I'm not going to put it on the slide just because it would be too long. But it's something, if you've never done it, to do yourself. If you've done it once, then you'll probably know how to do it and you'll be expecting the result at the end. So after we differentiate these and substitute them into the kinetic energy formula, we get the following. And again, if you've never done this yourself, maybe it's worth doing once. But if you have done this in another context, you can maybe just write down the final result. You'll have seen it before. Next example is the Lagrangian of a standard pendulum, which is shown here. Now the kinetic energy for this is a half m L squared theta dot squared. Here L is fixed, so that replaces R in the kinetic energy formula before, but because it's fixed, there's no L dot term. We only have the tangential component of velocity. Next, we want to work out the potential energy. So we're going to say y equals 0 is the top of the pendulum, and then the potential energy is mgy or mgh. And then we're going to rewrite y in terms of theta. So we're looking at the triangle. The distance from the top of the pendulum to the mass is L cos theta. And so our potential energy is minus mgl cos theta. And then our Lagrangian, we take the kinetic energy and we subtract the potential energy. And note, we could have said y equals 0 is the bottom of the pendulum instead of the top. We would have got the same result. That would have just shifted our potential energy by a constant. But shifting things by a constant won't affect our equation of motion. The next example is a bead attached to a rod so that it can slide freely up and down the rod. And then this rod is spinning with a fixed angular velocity. You can see this in the diagram here. I would recommend pausing the video and having a go to write down the Lagrangian yourself, and then come back to the video and I'll go through how to get the Lagrangian. So to get the kinetic energy, we have the sum of the tangential kinetic energy, which is r squared omega, and the radial kinetic energy, which is the r dot squared. And this just comes from the cylindrical coordinates. However, here it's maybe a bit different, because omega here is fixed. It's not theta dot, it's not a free coordinate, it's just a fixed value omega. So actually we only have one degree of freedom, one generalized coordinate, and that's r. And the potential energy is 0. You're in the horizontal plane. You could maybe rotate this and see what would happen if you had it in a vertical plane, and then our potential energy would include gravity. And that might be a different problem to do. So then the Lagrangian is just the kinetic energy. In this example, we have a pendulum, except now the top of the pendulum is free to slide horizontally while the pendulum swings. There's a diagram of it here. The difficulty with this is the best coordinates to use are theta, the angle of the pendulum, and x, which is the location of the top of the pendulum. However, writing kinetic energy in terms of these coordinates, it really isn't obvious. So in order to work out the kinetic energy, we're going to start off writing this in Cartesian coordinates. So here we have the kinetic energy, and that's just taking into account the horizontal and vertical velocity of the mass at the end of the pendulum. Then in order to turn these into x and theta, we need to rewrite the Cartesian coordinates in terms of our new coordinates. So the horizontal position of the mass, xm, is the horizontal position of the top of the pendulum plus the extra distance caused by the fact that the pendulum has swung out a bit. And the vertical position of the pendulum just comes from the angle of the pendulum. So subbing this in, we get the kinetic energy here in terms of x and theta. Then to get the potential energy, well, this is still just gravitational potential energy. This is exactly the same as in a normal fixed pendulum. So minus mgl cos theta. And then we put this all together and we get our Lagrangian. Now, how might this change if the top of the pendulum, rather than being free to swing around, was actually driven? So it was attached to a motor and it was driven back and forth at a fixed rate. How would this affect our Lagrangian? Well, we could leave the Lagrangian as it is. So the difference would be this x dot wouldn't be a coordinate. It wouldn't be a parameter we can get an Euler-Lagrange equation for. It would just be a known function. However, we could simplify the Lagrangian and get rid of this constant term here, or this just function here. Since it doesn't depend on any of the free coordinates, any of the generalized coordinates, we don't need it. We could just get rid of it. Our final example looks very similar to just a standard mass on a plane kind of problem, or block on a plane kind of problem. However, now the plane, rather than being an infinite or rigid or static plane, is more like a wedge and it's free to move. And so at the beginning, it seems like we have three coordinates to consider. Firstly, we have the horizontal position of this triangle, of this plane, as it slides back and forth. And then we also have the horizontal and vertical positions of the block, of the middle mass M. And so if you want to have a go by yourself, I would start by using these three different coordinates, but then because the small mass has to be on the surface of the plane, you can actually rewrite the height of the mass, so the y little m, in terms of the relative distance between the center of the wedge and the center of the little mass. So I would say pause the video and have a go, but I'll go through this one in a fair amount of detail since it's not easy. So we're going to start with the kinetic energy. And initially, using the initial coordinates, this is just the sum of the kinetic energy of the big mass and the sum of the kinetic energy of the small mass, where we've used both the x and the y coordinates at the moment. Then, in order to get rid of y, we substitute in our relation for y given in the hint, which hopefully you can have a go and find yourself. And then the potential energy is still mgh or mgy little m, except again we're going to rewrite y in terms of the horizontal positions of the mass and the wedge. And then finally, our Lagrangian is quite a long one. Our Lagrangian is given here. So, in summary, we saw the Lagrangian is kinetic energy take away potential energy. And the reason for this is that it recovered Newton's laws of motion after we applied the Euler-Lagrange equations. And as a problem-solving tip, I often think start by writing in Cartesian coordinates and then write your Cartesian coordinates in terms of some more natural coordinates. And then substitute the function of getting these Cartesian coordinates in terms of the more useful coordinates, and then substitute those into your kinetic energy and potential energy.